Hi, this is Tom Tolbert, Pulmonary and Critical Care Fellow, and this is the first video on mechanical ventilation. In this video, I'm going to cover the mechanics or the physics of breathing in, or inspiration, and the physics or mechanics of breathing out, or expiration. In order to understand how mechanical ventilators work, you have to understand how a normal person breathes in and breathes out, even when they're not on a mechanical ventilator. So that's mostly what I'll be covering in this lecture. Special thanks to Mira John, a resident who has been helping me with these lectures. In order to understand breathing, you have to understand flow. And all flow is a volume moving from one place to another in a certain amount of time. So it's a movement of volume over time. And anytime you take a unit like volume, or V, and put a dot over it, that's the same thing as saying over time. So a V with a dot over it is how we designate flow, because it means volume over time. Now, in order for a volume of air to move from one place to another, you have to establish a pressure gradient. And that's a difference in pressure between 2 points, right? So if this is point 1 over here and point 2 over here, if they're equal, there won't be any movement of this volume towards P2, right? Towards this second point. So in order to establish a pressure gradient, I could make pressure 1 larger than pressure 2. And if there's nothing blocking the movement of this volume of air over to pressure 2, then it will move over because pressure 1 is bigger than pressure 2. And because it's a movement of a volume of air, it's a flow. If it happens in a certain amount of time, then you divide by the time you get the flow. So if we said this was a liter and it took 2 seconds for it to go from 1 to 2, then we would say that the flow was half a liter per second, right? Because 1 over 2. Conversely, we could do the same thing not by making pressure 1 big, but we could make pressure 2 smaller, right? And that would do the same thing, because then pressure 1 could push the volume of air in this direction toward pressure 2. And that's a pressure gradient, and this is the direction of the pressure gradient. Pressure gradient is designated by delta P, and you can calculate delta P like this. So the pressure gradient is equal to the first pressure minus the second pressure. So because the flow is moving pushed by pressure 1, it's positive, and because the flow is against pressure 2 is negative. Another way to say it would be that pressure 1 favors movement in this direction, so we designate it positive here, and pressure 2 disfavors movement in this direction, so we designate it negative, so pressure 1 minus pressure 2. Let's say this is your lung. The object of ventilation, of breathing, is to get this tidal volume, designated like this, V with a subscript T, so this is tidal volume. You have to get this tidal volume into your lung and then back out again. So during inspiration, tidal volume goes in until the end of inspiration, and then expiration starts and the tidal volume comes back out. Throughout this video, it's going to be really important to know whether I'm talking about inspiration or expiration, because otherwise it'll be tough to keep things making sense. So to help with that, I'm going to keep this up here in this corner, and that way you can keep track of whether we're talking about inspiration or expiration. Of course, I'll try to remind you with what I'm saying, but this should make things a little bit visually easier. Going back to how volumes of air actually move, remember that you need a pressure gradient. So in order for this tidal volume to move into the lung, there has to be a pressure here, P1, and a pressure here, P2. And pressure 1 has got to be bigger than pressure 2 in order for this air to move in. If the tidal volume is moving into the lung, that's inspiration. So the pressure gradient favoring inspiration is P1 minus P2 here. And what are those actual pressures? Well, remember what we have to go through to actually get into the lung, right? So this is somebody who's not mechanically ventilated. This is just like a normal breathing person. They have an airway, right? From their nose into their mouth, down their throat into their trachea, down through the small airways into the lungs. That's all of this right here. This is the airway, okay? And that gets into the lungs here, but the lungs are surrounded by a chest wall, right? So lung here, chest wall here, this black box I've drawn around it. And then at the bottom of the thorax is the diaphragm. So this is the diaphragm here, airway, chest wall, lungs, diaphragm. The diaphragm creates a negative pressure. That's P-mus, or the pressure of the inspiratory musculature, which is large part the diaphragm. That muscular pressure, that negative pressure, transmits to the pleural space. And just to keep things straight, we're going to say what the pressure gradient direction is. So it's a negative pressure, it transmits to the pleural space, but since it's a negative pressure, this is the direction of the gradient, right? That negative pleural pressure transmits across the lung wall into the alveoli to create a negative alveolar pressure. That negative alveolar pressure transmits up the airway and makes the airway pressure negative. And finally, that negative airway pressure opens up to the atmosphere and acts on the volume outside your mouth so that you can breathe it in. Now you can simplify this whole thing by just removing these intermediate pressures and keeping the pressures on the ends, because it's the pressures on the ends that are driving the tidal volume into the lungs, right? That's the pressure outside the system and the pressure created inside the system to pull air into the lungs. So that's atmospheric pressure and muscular pressure. You can just sort of get rid of everything else just as long as you remember how muscular pressure got all the way up the airway, to know that it's atmospheric pressure and muscular pressure that drive that volume of air into the lungs. Now, atmospheric pressure we take as 0. That's just the pressure outside in the air, and that's our 0 point, or the reference point. So we just designate that 0. That simplifies this equation to negative P mus. But because the magnitude of pressure created by the diaphragm is actually favoring inspiration, we just simplify things by dropping that negative sign and saying that the pressure gradient for inspiration is equal to the pressure created by the diaphragm. And in most cases that's true. People breathe in large part in only with their diaphragm. There are exceptions to that, but for the most part the diaphragm is the inspiratory muscle, and it creates all the pressure needed to get a volume of air down into the lungs. And that's exactly what this is saying. Diaphragm contracts, creates that negative pressure, and the tidal volume moves into the lungs, just like that, until the end of inspiration. Just to drive this point home, I want to talk about what would happen if your diaphragm didn't work, if your diaphragm was paralyzed. If your diaphragm's paralyzed, then it can't flex. If it can't flex, it can't create any negative pressure, or pressure less than atmospheric pressure. And that means that P mus is gone, or the pressure favoring inspiration is gone. So your inspiratory pressure gradient is 0. If your inspiratory pressure gradient is 0, there's no movement of volume into the lungs. There's no flow of air into the lungs. And if you don't do something about that, you die, because that means you're not breathing. This was the situation during the polio epidemic in the early and mid 20th century. Kids would get polio and their diaphragm would become paralyzed so that they couldn't create any inspiratory muscle pressure and they couldn't breathe in. Now the diaphragm works by creating a pressure that is less than atmospheric pressure, and that's a negative pressure. So we breathe in by creating a negative pressure. They took that same concept and created the iron lung. And the iron lung was a big tube, essentially, that the patient lied in with their head outside the tube so that their mouth would be open and exposed to atmospheric pressure. The iron lung would create a negative pressure on the outside of the patient that would transmit across the patient's chest wall into the pleura. So you go across the chest wall here, this negative pressure transmits across the chest wall into the pleural space. So now the pleural space pressure is more negative. That more negative pleural space pressure transmits across the lung into the alveoli. That negative alveolar pressure transmits up the airway, and the negative airway pressure transmits all the way out into the atmosphere to act on a volume of air. If you simplify all of this by getting rid of all these intermediate pressures and just recognize the two pressures that are establishing this gradient, that is the atmospheric pressure and the iron lung pressure, you get essentially the same thing you had with the diaphragm, and that the pressure gradient favoring inspiration is created by the magnitude of the iron lung negative pressure. And that pressure gradient would drive a volume of air into the patient's lungs during inspiration. Because the iron lung creates a pressure that is less than atmospheric pressure, or a negative pressure, just like the diaphragm, it has been called a negative pressure ventilator. This is what an actual iron lung look like. You can see the patient's head is outside here, so his airway is open to the atmosphere, whereas inside here it's going to create a negative pressure that will transmit to his chest wall and all the way, into his alveoli, up his airway, and that will cause a volume to move into his lungs. I've kept things pretty simple so far by just talking about pressure gradients, about how you won't get a tidal volume moving into the lungs without creating a pressure gradient. That is, the diaphragm has to create a negative pressure in order to favor the movement of this air into the lungs, right? But there's obviously more to it than that. There are things that impede the movement of this air into the lungs. There are things that resist that. And those are two pressures that the diaphragm has to overcome in order to move a given volume of air into the lungs. The first is the airway resistance. Just by the nature of the molecules in this volume of air hitting the sides of the tube as it goes down the airway, that creates a resistance pressure, an airway resistance pressure that the diaphragm has to overcome in order to move this volume of air. The other thing is that the lungs and chest wall have a certain stiffness, so you have to create enough pressure to overcome that stiffness in order to inflate the lungs and the chest wall. So what we say is that the inspiratory pressure created by the diaphragm has to be equal to the resistance pressure of the airway, or the pressure of airway resistance, and the pressure created just by the stiffness of the lungs and chest wall. Let's break this down into its individual components. First, let's talk about the pressure created by airway resistance. I remember Ohm's law just because it helps me remember this. V equals IR, or the voltage of a circuit is equal to the current through the circuit times the resistance of the circuit. For flow through a tube, pressure is analogous to voltage. So the pressure created across the tube from one side to the other is equal to the flow through the tube times the resistance of the tube. Just by this airway having a certain diameter and a certain length, it has a certain resistance. And you can think about like trying to breathe through a straw, like a straw you would drink a soft drink with. If you tried to breathe through that, it has a high resistance, so it creates a lot of pressure, or you need a lot of pressure in order to breathe in and out. Think about that in contrast to a snorkel. A snorkel is much easier to breathe through. You don't have to create as much pressure because it has much lower resistance. So we can drop that in. P resistance equals flow times resistance here. Now the diaphragm has to create a pressure to get to a certain flow, right? That's what we want to do. We want to get a certain flow down through our airway, so we have to create a pressure to get to that flow. If it isn't obvious, pressure and flow are linearly related, right? So if you make a graph like this where you put pressure on the x-axis and flow on the y-axis, you'd have a straight line like this, right? So if this is your goal flow, this is how much flow you want to be going through this tube, in order to get to that goal flow, you have to create a certain amount of pressure, and that would be the resistance pressure, the resistance to flow through the airway, right, for this given tube. Now, say this is a snorkel, and this is the straw I was talking about before. Because this straw is so much narrower than this wide snorkel, the resistance is much higher, so this relationship changes. This line moves down. So that in order to get to that goal flow, in order to get the same amount of flow through this tube as through this tube, you have to create a much higher pressure. So the P resistance is much higher for this straw than it would be for the snorkel. So higher resistance means you need to create a higher pressure in order to get the same flow. For the stiffness of the lungs and chest wall, let's imagine a system in which there is no airway, it's just lungs and chest wall. What pressure would the diaphragm have to create to get this tidal volume into the lungs, right? So that would be the stiffness pressure, the respiratory system stiffness. And if you plot on a graph pressure on the x-axis and volume on the y-axis, and remember this is volume right now, it's not flow because it doesn't have a dot, it's just a V. So this is volume, not flow. In order to get this tidal volume, this is like your goal tidal volume into the lungs, you'd have to create this much pressure. Right, so you have to get to this much pressure in order to get this tidal volume in the lungs. If I were to put a bowling ball on your chest, I would change this whole relationship because your system would be much, much stiffer, right? It would take a lot more pressure to get any volume of air into the lungs than if you don't have a bowling ball on your chest, right? So this makes the system much stiffer. The line here, its slope decreases, right? So this has like a high slope, this kind of a lower slope. To get to this same tidal volume, you have to create a lot more pressure, right? So the same volume is put in both of these systems, but the diaphragm would have to create a lot more pressure in this system with the bowling ball than in this system without the bowling ball, because this is a much stiffer system, and therefore the stiffness pressure that the diaphragm has to overcome is much higher. This relationship of pressure and volume, this slope, is defined as compliance. So compliance is equal to the tidal volume divided by the stiffness pressure, right? So, or rise over run. If you took the rise in volume over the run in pressure, you get the compliance. So volume over pressure equals compliance. You can solve for stiffness, right? And you get tidal volume over compliance. So the stiffness pressure of the respiratory system is equal to the tidal volume divided by the compliance. And we can put that into our expressions down here, right? So for this system, it has a high compliance or a high slope, meaning it doesn't take very much pressure to get to your tidal volume, right? So this is a high compliance system. Whereas this system here is a low compliance system. It takes a lot of pressure to get to the same tidal volume. So this system has low compliance or it's very stiff. Now we could put everything together. So we have an expression for the resistance pressure, the pressure created by the resistance of flow through the airway, and a stiffness pressure, or the pressure needed to overcome the stiffness of the chest wall and the lungs in order to get a tidal volume in. If we put these together, we find that the pressure that the diaphragm has to create is equal to the flow times resistance for the airway, and then for the stiffness, it's the tidal volume divided by the compliance. This expression is often called the equation of motion of the respiratory system, and it's fundamental to understanding how we breathe in and how a ventilator helps us breathe in. I'm just going to move that aside for now and to keep track of everything. Remember that the muscular pressure created by the diaphragm to inspire has to be equal to the resistance pressure and the stiffness pressure, which is equal to the flow times the resistance through the airway, or the tidal volume over the compliance of the lungs and chest wall. So keep those equations in mind as we talk about the rest of this. So let's say we intubate this patient. So now this patient has an endotracheal tube in, and they're connected to a mechanical ventilator. So here's the inspiratory tubing here in this dark blue, and the expiratory tubing is right here in this light blue. As part of the airway and part of the pressure created by resistance to flow through the airway, you now have to include everything down the inspiratory tubing, through the endotracheal tube, through the patient's airway, all the way down into the respiratory bronchioles. That's all considered part of the airway now. So now this resistance pressure has to be overcome. You've changed the resistance, so the flow is going to create a different pressure than before, than without being intubated. There's going to be a higher resistance to flow. Unlike the iron lung, which was a negative pressure ventilator, this ventilator is a positive pressure ventilator, meaning it creates a pressure that is greater than atmospheric pressure, and that's P-vent. P-vent is a positive pressure, and it transmits down the airway, so down all these tubes, down the endotracheal tube, down the patient's airway, all the way down into the patient's alveoli, right? So that positive pressure here transmits down the airway, positive pressure in the airway transmits into the lungs. And at the same time, the diaphragm could be flexing to create a negative pressure, and these two pressures working together, the positive pressure of the vent and the negative pressure of the diaphragm, are both working to overcome these two pressures, right? The resistance pressure and the stiffness pressure, to help inflate the lungs. Right? We can simplify things by getting rid of, the airway pressure and the alveolar pressure, remembering how we got from here down into the lungs. But it's really the ventilator positive pressure and the diaphragm negative pressure that both work together to create a gradient favorable to inspiration. So we depict both of them as positive here because they're both favoring inspiration. So this is the equation of motion for inspiration when you're on a mechanical ventilator. The positive pressure created by the vent and the negative pressure created by the diaphragm both work together to overcome the airway resistance pressure and the stiffness of the lungs and chest wall in order to inflate the lungs. And that's what happens. This tidal volume moves into the lungs, working with both the vent and the diaphragm. An analogy here might be helpful just to sort of put everything together. Imagine that the work of inspiration, or the work of actually getting a volume of air into the lungs, is lifting up this bucket. So this is the diaphragm. Its whole job is to get air into the lungs. Its whole job is to inspire. So it has a rope here that's connected to the top of this bucket, and if it flexes, it lifts the bucket up. Part of the work of inspiration is overcoming airway resistance, or that flow times resistance expression. So we add that to the bucket. That's the pressure the diaphragm has to create in order to create a flow down the airway. And then the other part of the pressure that the diaphragm has to create is to overcome the stiffness of the lungs and chest wall. So that's a given tidal volume over the compliance. We add that also to the work of inspiration. So to put everything together, the work of inspiration is the same as that equation of motion that we talked about. The resistance pressure plus the stiffness pressure is equal to the flow times resistance plus the tidal volume over the compliance. The diaphragm flexes and pulls the bucket up. So the diaphragm is pulling in order to accomplish inspiration. On the other hand, the ventilator also helps with inspiration, but it's pushing up on the bucket. So the ventilator creates a push in order to push the bucket up, while at the same time the diaphragm is pulling in order to pull the bucket up. If the diaphragm is paralyzed, then it can't accomplish any of the work of inspiration, and it's entirely up to the ventilator, which can still create enough positive pressure, but it has to create more because the diaphragm isn't helping at all, right? On the other hand, if you were to set the inspiratory pressure on the ventilator to 0 or make P vent 0, then the diaphragm would have to do all the work and the ventilator wouldn't be pushing the bucket at all. With modern positive pressure ventilators, when you aren't paralyzing patients, you're often somewhere in between the extreme of a paralyzed diaphragm and the extreme of the ventilator not providing any positive pressure at all. So the diaphragm and the ventilator are working together. The diaphragm pulls, the ventilator pushes, and the bucket moves up, right? And that's just to say that the diaphragm and the ventilator are accomplishing a job together by working from different directions. The diaphragm pulls air in, whereas the ventilator pushes air in. So the diaphragm creates a negative pressure, and the ventilator creates a positive pressure, but they're both creating pressures to do the same job, and that's to accomplish inspiration. Up until now, we've been talking about inspiration. Let's talk about expiration. How does expiration happen? Well, obviously, you have to get this tidal volume back out of the lungs into the atmosphere after you've done your gas exchange, right? After you've put your CO2 in here and taken the oxygen out. You have to get this tidal volume back out so you can get the next breath in, right? So how does that happen? Well, obviously there needs to be a pressure gradient in order to move this volume from here inside the lungs to outside here in the atmosphere. And because the atmosphere is downstream, it's going to be at the end of this expiratory pressure gradient, right? Also, the airway is going to resist flow this way, right? You're going to have to create a certain amount of pressure in order to overcome the friction of resistance to flow through this airway. So again, that's going to not favor movement of air this way, so that's a negative thing. So what is it that actually creates the pressure on this side in order to push the air out? It's not the diaphragm, because the diaphragm is an inspiratory muscle, so it's not working during expiration. So PMUS here is 0. What is it then? Well, the lungs and the chest wall have recoil. So when we inspired, we stretched the lungs and the chest wall out, right? Meaning they have like an elastic energy in them. And that elastic energy allows them to push back on the volume of air that's inside the lungs. So this chest wall recoil pressure is going to transmit to the pleura, right, and create a positive pressure. That positive pressure in the pleura is going to transmit to the alveoli. At the same time, the pressure from stretching out the lungs, the lung recoil pressure, is also going to transmit to the alveoli. So now you have a positive pressure here inside the lung, inside the alveoli. That's going to transmit up the airway, and that positive airway pressure is going to transmit out into the atmosphere. So all the way from the chest wall recoil and lung recoil pressures, that transmits all the way through the lungs, up the airway, and out into the atmosphere, and that's how you create this expiratory pressure gradient. Just as before, we can simplify all this and take away all the intermediate pressures and just say that the expiratory pressure gradient is created by the lung and chest wall recoil pressure minus the resistance pressure from flowing through the airway and the atmospheric pressure. But lung and chest wall recoil is the same thing as the stiffness pressure, that volume over compliance. So to get this tidal volume into the lungs, the diaphragm had to create enough pressure to overcome the stiffness, right? So that was the pressure of stiffness. And that stiffness pressure is created by the lung recoil and the chest wall recoil. And the big point is that you create the pressure for expiration during inspiration, right? You do that by when you drive that volume into the lungs and chest wall, it stretches out the lungs and chest wall. And by stretching it out, it stores some energy. And so that's all the energy that's needed when the diaphragm is done contracting and when you're no longer inspiring. You use that energy that's stored in the lung and chest wall recoil to push the air back out. And that's what we mean when we say that expiration is passive. You don't need another muscle. All you need is the diaphragm, because the diaphragm stretched out those things during inspiration so that the lung and chest wall can recoil during expiration and push the air out. We can simplify this by getting rid of the chest wall recoil and lung recoil expressions here and recognize that atmospheric pressure is equal to 0. So you get this simplified equation for the expiratory pressure gradient, or the gradient of pressure that favors moving this volume of air from the lungs out into the atmosphere. That's going to be the pressure created by the stiffness of the lungs and the chest wall minus the pressure created by the flow of air through this airway. And those two things operating together allow this volume of air to be expired. This is important to remember. I think a lot of the time we think about inspiratory pressures when we talk about mechanical ventilation without thinking as much about expiratory pressures. So even without thinking about mechanical ventilation, just think about somebody who has COPD or asthma, for instance. Their airways are really narrow, so they have really resistant airways, meaning that there's a lot more pressure that's needed to overcome the airway resistance than somebody who doesn't have asthma or doesn't have COPD. And especially with people with COPD and emphysema. So with emphysema, you destroy a lot of your lung tissue, meaning your lungs don't recoil as well. So this stiffness pressure is lower. So not only do you have a higher airway resistance pressure that you need to overcome if you have COPD and emphysema, you also have a low stiffness pressure. And the whole thing, putting it all together, might mean that you can't generate enough pressure to move your tidal volume out of your lungs without also flexing some muscles. So you'll see that in people with COPD, that they can't breathe out sometimes just passively. They have to flex like their abdominal muscles, or they have to flex their intercostal muscles in order to actually breathe out, because this stiffness pressure is not enough to overcome this increased airway resistance pressure. I want to make a last point about expiration that can be kind of subtle and difficult, but it's important. So during inspiration, you got this tidal volume down into your lungs, you stretched out your lungs, stretched out your chest wall. That creates recoil, and that recoil creates a stiffness pressure that's enough to overcome the airway resistance and push that tidal volume down the airway out of the lungs, right? So here we are at still in expiration, and let me zoom in on this to make it a little bit easier. So we're still in expiration, but now the tidal volume has completely come out. There's no more tidal volume left in the lungs to come out. So since the lungs and the chest wall are now no more stretched out than they were before inspiration, there's no more recoil left, right? There's no lung recoil or chest wall recoil left to drive any further airflow out. And that means that the stiffness pressure is gone. The stiffness pressure is now 0. At the same time, if there's no air moving through this tube, through this airway, then there's no resistance pressure. And since nothing's moving, there's no resistance pressure. So P stiffness, P resistance, both 0. There's no more gradient favoring expiration, and everything just stops moving. The tidal volume is outside of the lungs, and there's no more tidal volume to come out. There's no more flow. Everything just stops moving. This is end expiration, and this is important. So during end expiration, there's no resistance pressure, there's no stiffness pressure. You just drop those out. This is important because at this time, there's no pressure created by the flexion of the diaphragm. There's no pressure created by the flexion of expiratory chest wall muscles or abdominal muscles. And there's no pressure created by the recoil stiffness of the lungs or the chest wall. Why is this important? Well, say you wanted to do a measurement inside the pleura here, or you wanted to do a measurement in the heart by putting like a Swan-Ganz catheter in the patient to measure the pressures in their heart. You wouldn't want your measurements to be affected by the diaphragm or the chest wall stiffness or the lung stiffness or by the patient making expiratory efforts, right? So you'd want to do it at a time when all those things were gone. And that's this period. End expiration is often when we do measurements inside the heart or inside the pleural space in order to get consistent readings. The other reason this is important is because there's no more gradient between the atmosphere and the lungs and the airway, right? Meaning there's no greater pressure here or greater pressure here. That means alveolar pressure is 0 and airway pressure is 0 or equal to atmospheric pressure, right? This can create some problems due to gravity. So gravity pulls down on the chest wall as well as all the tissues inside the chest. And what that can do is actually create pleural pressures down here where there's all this tissue on top of the pleural space right here, right? And if this patient is lying down and gravity's in this direction, there's a bunch of tissue up here that's pushing down here, right? And that makes the pleural pressure here potentially higher than the alveolar pressure. So this pleural pressure is not 0, and this alveolar pressure is 0. And what can happen there is you get compression on these parts of the lungs, right? So this pleural pressure pushes on these parts of the lungs, and you get lung collapse or atelectasis. The other thing that can happen is that there's tissue on the airway, right? So if you're lying down, like your tongue or your soft palate can be pushing down on your airway by the effects of gravity, meaning the pressure created by the tissue is greater than 0. So that can cause the airway to collapse because the tissue pressure is greater than the airway pressure. What could you do to avoid atelectasis, to avoid the lung collapsing from higher pleural pressures than alveolar pressures, or to avoid airway collapse from this soft tissue sort of pushing down on the airway? How could you avoid this? Let's say instead of having the patient breathe at atmospheric pressure, just breathing on their own, let's put them on a non-invasive ventilator. So this is a non-invasive mask they're wearing over their nose and mouth. And let's apply a positive pressure during expiration, which is also known as PEEP, or positive end expiratory pressure. That might seem sort of counterproductive because now the expiratory pressure gradient is being fought against by this PEEP, right? So the gradient favoring the movement of this air from in here to out here is the stiffness pressure minus the pressure created by the airway resistance minus the PEEP, right? And now it's not atmospheric pressure, it's not 0, it's positive, so it's countering expiration. And that might seem counterintuitive. Still, as long as PEEP is not greater than the stiffness pressure, you should get movement of air out, and the benefit of PEEP becomes clear in end expiration. What happens is that you still have the effects of gravity. So gravity is pulling down on these tissues, and that's creating positive pleural pressures here in the chest wall, and also positive tissue pressure above the airway, which previously we talked about could cause airway collapse or lung collapse and atelectasis, right? But since you're applying a positive pressure now, or a PEEP, this airway pressure is also greater than 0, and the alveolar pressure is greater than 0, even though nothing's moving anymore. The tidal volume is done being expired. You're keeping this airway pressure elevated, right? And that keeps the airway from collapsing, and it keeps the alveoli from collapsing into atelectasis. So that's where most of the benefit of PEEP comes from, is it keeps your lungs from collapsing with atelectasis, and it keeps the airway from collapsing like in sleep apnea. Let's summarize what we've learned. During inspiration, the diaphragm flexes. That creates a negative pressure that overcomes the stiffness of the chest wall and the lung, as well as the resistance to flow through the airway to drive a tidal volume into the lungs. During expiration, the lung and chest wall have a recoil that creates a stiffness pressure that overcomes the resistance to flow through the airway out in order to drive this tidal volume back out. And it's a passive phenomenon. There's no flexion of any muscles. It's just by the nature of the stiffness of lungs and chest wall that drives that tidal volume back out of the lungs. Once that tidal volume has been expelled, and the lungs and chest wall are no longer creating any stiffness pressure because they've fully gone back to their unstretched states, you're at end expiration. There's no more movement of air, and there's no pressure gradient between the lungs, the airway, and the atmosphere. And so nothing moves during end expiration. Everything's relaxed. Adding a mechanical ventilator to the system, whether it's a non-invasive mode like I've depicted here, or whether the patient's endotracheally intubated, the principle is the same, allows the ventilator to provide a positive pressure during inspiration, or P-vent, that helps drive a tidal volume into the lungs. And that can take over completely for the job of the diaphragm, or at least assist the diaphragm, which is trying to pull the tidal volume in while the vent pushes the tidal volume in with the positive pressure. During expiration, or at the beginning of expiration, the vent stops providing that positive pressure and the diaphragm relaxes. And just like if you weren't being mechanically ventilated, expiration occurs passively from the stiffness of the chest wall and the stiffness of the lungs, creating a pressure that drives this tidal volume back out. One of the benefits of mechanical ventilation is that you can keep the airway pressure and the lung pressure positive even in end expiration, and that's positive end expiratory pressure, or PEEP. And this can keep the airway from collapsing in the case of like obstructive sleep apnea, and it can keep atelectasis from happening due to the gravitational effects on the tissues inside the chest wall. Thanks a lot for watching. I hope you found this helpful. Please let me know what you liked, what you didn't like, what could be improved or made clearer. There will be more upcoming videos on mechanical ventilation. I think the next one is going to be about phase variables, or how the ventilator identifies when a patient is trying to breathe in versus when a patient's trying to breathe out, so that the vent can sync to the patient. Stay tuned.